So, in the last class we learnt how to analyze the complexity of algorithms. Now, we will take some somewhat more serious examples. We will take the problems of sorting and searching. You might have already learnt that selection sort, bubble sort, insertion sort in your college, and quick sort and merge sort are faster algorithms. So, what we will do is we will take one linear sorting algorithm, which is selection sort, and then we will look at quick sort first, and then we look at some searching algorithms also. So, let us say I have given an array here. What is the objective? You have an array which is unsorted, and the objective is to produce an array that is sorted. I just started the indices from 1 to 8 here, just to although in C it starts from 0 through 7, just for when you look represent it as a set of numbers in pseudo code, you would write it starting from index 1, okay, and you want this output. Whereas in searching, what do I want to do? I have given a sorted array, I am given a key 12, let us say, and I want to find out whether the key is present in the array or not. It should return the location where the particular key is present. In this example, for example, when I have given key 12 here, it should return the index 4 on the searching example. So, the selection sort algorithm is a very simple algorithm, and I have used again the swap to do this. It is not required though, but nevertheless it is not very efficient. Let us say I have an array like this. I am just taking some arbitrary array. What you do in selection sort is, let us say this was 10, 25, 2, 6, 12, 13, 8 and 7. Okay. I have written it a little inefficiently in that piece of code here, it does not really matter. So, start with this, and then I compare this element with all the elements in the array. So, I have a pointer I here, a pointer j, which goes through the entire array. Then I find out which is the most minimum element, and I put that element in the first position. So, 2 goes here, and 25, 10, 6, 12, 13, 8, 7. I have written a slightly more inefficient version in the notes because whenever I see two numbers which are that a smaller number is seen, I just exchange them. That is not required actually, you just need to find the location of the smallest element. So, now I know that the most minimum element in this is the first position. Next, what do? I start with this element. So, this is my pointer I have the pointer j, which again goes through the length of the array, finds the most minimum element. This is 6 over here, put 6 here and 25 goes here. So, you get the idea. So, repeat this process until what happens? Finally, the last 2 elements, for example. So, initially it is being this j loop, for example, goes from, let us say, index 1, 2, 3, 4, 5, 6, 7 and 8. The first time the j loop is executed 7 times, next time it is executed 6 times, and so on until it, for example, for j equal to, until it becomes the size of the array which we need to process becomes 1, we have to keep repeating this. So, basically if you look at the depth, for example, next after this 2 and 6 have been processed, we are starting here, and then I compare with these elements and I find 8 is the smallest element, 2, 6, 8 over here, 25, 12, 13, 10 and 7 is what you are going to have. Okay. So, 3 elements are already sorted, and then you look at this part of the array, again j goes from this point until n. I keep repeating this process. So, what happens is the size of the array which needs to be sorted keeps on decreasing from iteration to iteration, and the size of the sorted array also gets incremented by 1. But notice that the time that I am going to take, the first time I am making n minus 1 comparisons, then I am making n minus 2 comparisons, n minus 3 comparisons, and if I count through all of them until finally I make one comparison, the time complexity of this algorithm is going to become order n squared, where n is the size of the input. What is the size of the input here? Is the length of the array. Okay. So, I just given this program in C over here. So, notice this is comparison, assignment and increment. I say order 1, this is order 1, all these are order 1, But what happens is this loop, for example, if you write it in terms of time complexity, it is order n. Again here I have two program segments, this assignment takes order 1 and this takes order n, therefore it is like a sum rule, it becomes order n, and then this for loop is executed order n times, so therefore it becomes order n squared. So this is the program of the form P1 into P2 into P3. Outermost for loop is P1, inner for loop is P2, and then within that there is a program P3. Okay. So this is how you compute the time complexity of selection sort. This is a bit inefficient. So what we do is we do a slightly different algorithm called the quick sort algorithm, and what we do in the quick sort algorithm is the following. We do it a little differently. Start out with this, and what we say is, let us start with 2 pointers. We define what is called some pivot element. Okay. Just for convenience, I am going to take the 4th element as the pivot element. Let me call it the pivot element. Then you have 2 pointers I and j. Okay. Then what do we expect? The pivot element is 6. So what you do is you keep moving the pointers I and j until you come across an element which is larger than the pivot element on the left hand side, and on the right hand side you come across with until you find an element which is smaller than the pivot element. So initially itself you are having this, then what you do is you simply exchange them. When I exchange these two, I will get here 7, 25, 2, 6, 12, 13, 8 and 10. Okay. Next what do? I move forward, 25 is still larger than is larger than 6, and 8 is the same size, is larger than 6, so I ignore this. I keep moving forward, and what do I find here? Actually 6, for example, it is not smaller than 6, but it is not larger than 6 either. So what I do is 25 will move here and 6 will come here. Then I come across this, and clearly this is smaller than 6, so I leave it as it is. Now what this does is it divides the array into 2 parts, where one part consists of elements which are less than or equal to 6, another part consists of elements which are larger than 6. Then on each part again I repeat the same process, find the pivot element again, and then make the movements. For example, here again pivot will be 6, then notice that 7 is larger than 6 and 2 is smaller than 6, so 2 comes here, 7 goes here, and I repeat this. Then again what happens? The array will get divided into 2 parts, then again I stop when the array size becomes 1. That is what the pointers cross for that matter, and that is exactly what is being done every time over here. So what we are doing is, if left is less than j, so basically we have 2 parts here, left and right of the array are passed as argument to the quick sort algorithm. I is assigned to left, j is assigned to right. We are choosing the pivot element as a middle element here, this need not necessarily be so. Then what are we doing? When array I less than x, I am incrementing the array I. Then while x less than array j, I am decrementing it. Then if I is less than or equal to a, the 2 pointers have not crossed, then what are you doing? We are performing an exchange over here. Okay. Then we decrement and this, and what are we doing? Until the 2 pointers I and j cross, because once they cross, that means I process the entire array once. Then what do? If left is less than j, that means the number of elements is more than 1, then I call quick sort again with a new left value and new j value. Similarly, I call quick sort again with the new I value and the new right value. So when I keep doing this, if the array is if the quick sort algorithm is very good, then what you will find is the array here, for example, of size 8 will get divided into 2 parts of size 4, which will get divided into 2 parts of size 2, which will finally get divided into 1 element arrays, and the algorithm will terminate. So what you see is that we saw that the selection sort was an n squared algorithm, but here what we are going to see is that this quick sort algorithm is order n into log n. Let us see why this happens. In each this is, let us say, the first time I am looking at the array, this is the second time, the third time, the fourth time. Assume that it is an array of size 8. So, the first time I am looking at the array, I am looking at n elements, then it divided into 2 parts, 4 and 4. Then again, for example, these 4 elements have to be processed, these 4 elements also have to be processed. The next 2 elements, again all the 8 elements have to be processed, and here finally all the 8 elements. So, when you look at it, what is happening is that the depth of this recursion, how many times the recursive call is going to be executed, is only log n, and every recursive call means I am processing all the n elements. Therefore, the time complexity is order n log n, okay, of this quicksort algorithm. There are other sorts like the merge sort. Quicksort of course has a worst case time complexity of order n squared, we will see why. So, for example, what we do is, just as we saw the recurrence equation, we write the recurrence equation, let us say the best case, T of n is divided into 2 T n by 2 plus C n, because all the n elements are processed, T of 1 is equal to D. So, in general, quicksort analysis, it divides into 2 parts, T of I and T plus n and T of n minus I. Remember, in the example we had one array of size 3 and another array of size 5, this is what it will be. So, worst case what can happen, the depth can become, every time it divides the array into 2 parts such that the only one, it divides into 2 parts such that there are n minus 1 elements and 1 element, and this again let us say divides it into 1 element and n minus 2 elements. Then this depth will go down up to n, and the time complexity instead of being order n log n will become order n squared. Okay. So, this is about the sorting algorithms that we have looked at. Now, we look at searching. We will look at simple linear search and binary search. What is linear search now? We have an array which is already sorted, going back to this example that we have here. We have a sorted array, we are giving a key and we have to find the location of the key in the array. Okay. So, let us do linear search. So, what am I going to do? While I less than n and not found, if array phi equal to key found equals 1, else I plus plus return I, return found. Basically, it is telling you the key is found or not found. Okay. So, there is a very easy program. Of course, it is not capitalizing on the fact that the array is already sorted, because I could have also checked if the array is greater than key, and you could have also exited. But nevertheless, in the worst case, if I am using this is called a linear search algorithm, I have to search through all the elements in the array. Let us say even if it is sorted 2, 10, 15, 16, 30, 35 and 40, let us say, and I am looking for the element 40, then you have to process, you have to check with every one of these elements whether the key 40 is there or not. Therefore, the time complexity in this case, notice that there is a while block I less than n, order 1, all these are comparisons are order 1, assignment is order 1, increment is order 1, but the while block, for example, this is a program of the kind P1 into P2 and this runs n times. Therefore, the complexity is order n. All right. There is another better way of doing it if the array is already sorted, and this is the binary search algorithm, and the idea is basically the following. What we do is, let us say I have a sorted array like this. What we do is we divide the array into 2 parts. Let us say this is 1, 2, 3, 4, 5, 6, 7 and 8. Find index of the middle element, which is 1 plus 8 by 2, which is equal to 4, and then let us say I have given the key 12. I compare it with this middle element. Clearly, it is less than 12. That means it is not likely to be found in the right of the array. It is likely to be found only in the left of the array. So, what we do is, that means I can restrict my search to only this part. So, what do we do next now? We divide this part again 15, 16 into 2 parts. What is the middle part now? 10. Okay. I compare it with 10. It is larger than 10. Therefore, it must be only in this part. Okay. And what is this now? This indices are 3 and 4. Therefore, this is the middle element now. I compare it with 15 and clearly the number is less than 15 and it is not there in this part. Therefore, the key is not found in this array. Okay. So, how many times did we execute it now? This is the first time I divided it into half, then again we divided it into half and we divided it a third time. So, what happens is in this particular example we find that binary search is executed actually only log n times. Let us see this. So, here again remember how we did complexity analysis, order 1 here, comparison is order 1, is greater than adder of the middle element, then we are doing binary search, this is going to take order log n time, and here this again is going to take order log n time, k equal to lower, then I am just returning back the location and so on and so forth. So, each recursive call divides the order into 2, this recursion is what makes it log n because it is going to be executed log n times. The recursion terminates when the array size becomes 1 and the number of recursive calls is log n. Therefore, the time complexity is order log n to the base 2. As I said, best is to draw the recursion tree whenever you have recursive algorithms to solve for. So, basically what did we see here? Array got, so I started out with 8, then it goes to 4, then it goes to 2, this becomes 1. Okay. So, basically 1, 2, 3, 4, my n is 8, therefore, it is order of log of 8 to the base 2, the number of computations. Okay. So, this is how you solve the time complexity of programs. We have looked at recursion, we have looked at sorting, we have looked at searching algorithms and we have analyzed the time complexities. So, we are now ready basically that we have also learned the basic data types and the basic control structures that are there on programs. You did it in the C programming part and I just reinforced it in this part of the course, of a quick reinforcement. And basically now next what we are ready to do is how do I combine all these small data types like float, integer, char, array and functions, okay, to solve better problems. Can I think of a nice data organization which will enable me to solve the problems better, and that is the part on abstract data types which we will talk about. So, we will start with this in the next class.